Good evening, everyone, and welcome to the Amateur Radio General Class, session number 10. During our previous session, we discussed the concepts of modulation. We looked at amplitude modulation, or AM. We discussed modulation envelope. Then we talked about single sideband, or SSB. We also discussed the consequence of overmodulation. Then we went into a couple other modes, such as frequency modulation, or FM. We discussed phase modulation, or PM. And then we also talked a bit about FSK, or frequency shift keying, and specifically the mode called RITI. Then we discussed what phase shift keying is, or PSK. And then we went on to talk about QPSK31, as well as FT8 mode and the WSJTX software suite. And then we ended by discussing link margin and link budget. So this evening, we have quite a bit of material to cover. So we will be discussing the concept of heterodyning. We'll talk about image response, what is intermodulation. Then we go on to talk about the concepts of deviation and that of multipliers. We will also talk about bandwidth as it relates to frequency modulation. Then we will briefly touch on what duty cycle is and why it's important. Then we will also discuss the concept of symbol rate. Then we move on to talking about filters as it relates to noise. And then we will go to a couple of modes such as PSK31, RITI, WSPR, FT8, which are all digital modes. Then we'll discuss the concept of a frame and the part that's called a header. Then ARQ and NAC, and also forward error correction, or FEC. Then we'll discuss what is a waterfall display, and that will be it for this evening. So just quickly again, for persons who have just joined or looking at the live stream on YouTube, this is the level 2 in the amateur radio class under the FCC system. But we do have the previous course level, level 1, which is a technician class. And on your screen are the links to the playlist of the videos as well as all of the material. So that's level 1, the technician class course. So let's discuss where we are in respect of our curriculum. We are presently on signals and emissions. We will just about complete this evening, so we'll be going a little bit longer than usual, a little bit over the hour, just to almost complete. We just have a couple more things under signals emissions, but we'll, for all intents and purposes, finish most of that today, so that next week we'll just wrap up and then continue on to the next topic of antennas and feed lines. So again, please continue doing the practice exams, links on your screen. Okay, just that repeated slide about Zello. And most importantly, persons still continue to ask, where can I get the recordings, right? So folks, all of the recordings are available, as well as all of the material available at these 2 links here. So become quite familiar with these. We also send a weekly email to remind persons of these links. These are the most important links for this level 2 class or the general class course. All of the material available from these 2 links. Right, so we are using the No Nonsense General Class License Study Guide. I see a couple of students have actually received their copies. So great. We had no outstanding questions from last session, so we can go straight into the technical topics this evening. So previously we had discussed, what a superhet or a super heterodyne receiver was, but we didn't really discuss much about what heterodyne or heterodyning is. So we will deal with that, and hopefully that will pull things together from some previous sessions when we did talk about superhet receivers and the different stages and what makes up a super heterodyne receiver. But what is heterodyning? It is really just a fancy word to mean mixing. Mixing of what though? It's like you're baking a cake and you mix 2 ingredients together, right? So you have maybe flour and sugar, or flour and butter, or sugar and butter, whatever it is you're mixing. So you have 2 frequencies, because we're talking about amateur radio. So the things that we mix are radio frequencies or signals, radio signals. We mix them electronically inside of the device, inside of your receiver, your transceiver, your transmitter. We mix And that's how we produce additional signals, or that's how we do some processing of our signals. So heterodyning is simply the mixing of two radio frequency signals. So on the top right-hand corner of your screen, you will have a frequency going in, and this is the symbol for the mixer. So one frequency comes in, maybe the frequency that you're receiving, and then you mix it with another frequency. So sometimes you have something called a local oscillator that's generating a frequency. You mix them. And when you mix them, you end up with two products. One is the sum, and the other one is the difference. So you add the two frequencies together and you get an output, and then you subtract the two frequencies, one from the other, and you get another frequency. So these are the two outputs. Now, typically, you would be finding one more useful than the other, right? So sometimes the different frequency is what you are interested in, and you discard or filter out the sum frequency or the output. So you have the input, one frequency, as well as another frequency, and you have the output. So that's what mixing or heterodyning is, that technique that we use with the radio frequency signals. So let's get to this block diagram here that shows a particular receiver, right? So you have an antenna, it passes through the receiver stages, and then you end up with audio coming out in your speaker. So this is why it's a receiver. But if we look inside of a receiver, this block diagram, you'll see that the signal ends up going into a mixer, and then we have something called a local oscillator, which we have previously discussed. And the mixer takes the signal that we're interested in receiving, but what we're interested in is not so much the signal itself. We're interested in intelligence that's accompanying it, right? So not just the carrier, we're interested in the audio that has been encoded or modulated onto that signal. But to get that, we have to mix it and mix it down so we'll get an intermediate frequency, because the rest of the circuitry, remember, we could be using a receiver to receive a range of frequencies, but we need a very efficient detector here. So what we do is we mix the two frequencies together, the one that we're interested in plus our local oscillator frequency. So we end up with a frequency called IF, or intermediate frequency, and that is what we actually receive. And it's a much lower frequency. So therefore the circuitry here could be built a lot cheaper, and you can also have different stages and process that signal a lot better, rather than keeping it at the frequency that you're receiving the signal. So it's kind of down converting the frequency in a way. You could think of it that way, by mixing. So we end up with what is called the intermediate frequency, or what is commonly in radio speak called the IF stage. And in a radio, in a receiver, good quality receivers could have multiple IF stages as well, right? So anytime you have the IF stage or intermediate frequency, that's what you're doing. You're mixing the signal you're trying to receive with a local frequency. And the whole idea behind it is you want to actually end up with the same frequency at the IF stage. No matter what your input frequency is, you want to end up with a particular frequency here. So that's why the local oscillator, when you tune your dial, you're generating a frequency here to match the input, so that you will always get the same output when you subtract the two frequencies. And that's what we're interested in doing here. All right. So that's what we say in the last one here, that the local oscillator, which is this, when we mix it with the input frequency, we ensure that the same frequency is obtained on the output. That's why when we tune our receiver, we are actually changing what the local oscillator is generating, just so that we match the input frequency that we're interested in to end up with the same output. So this is another expanded view. You have our radio frequency, or transceiver or receivers listening to another amateur radio operator. So we have that input RF signal that's coming in from the air, received by our antenna, and it's going to the mixer stage. And then we have our local oscillator that we tune using our dial, or that's what we're actually doing when we're tuning that dial, either a push button or maybe some sort of a dial that we turn left or right. And they're mixing to end up with the intermediate frequency. And we want to make sure that frequency is the same no matter what frequency we are trying to receive. All right. So heterodyning. So let's actually give an example. We have just talked about it conceptually, but let's put some numbers so we could hopefully understand what this mixing thing is about. So we did say that the whole idea behind the mixer or heterodyning is that we want to bring in a frequency that we want to receive. So we actually put a frequency of 14.250 megahertz. That's the frequency on HF that, as a ham radio operator, we're trying to receive. We are also trying to achieve a case where the output from the mixer will always be 455 kilohertz or 0.55 megahertz, right? We always want the output from here to be that 455 kilohertz. Why? Because the circuitry that follows will be tuned, very well tuned, specialized circuitry that is tuned for that frequency. We don't want that circuitry that comes after to deal with any other frequency, because then we'll have to it'll have to be a lot more complex, right? It'll be more expensive. So we want the output from here to just be that frequency, because at the IF stage, that's the only frequency we want it to be able to listen or tune it to, right? So let's think of it that way. But to achieve that, we need to mix the frequency that we are trying to receive here with another frequency, right? So look at it this way. If I'm receiving 14.250, I need to mix it with some frequency that makes sure that the difference will always be 455 kilohertz. I may want to listen to another frequency, maybe 14.240, but I still want the output from the mixer to be 455 kilohertz, right? So I always tune this local oscillator such that the frequency it produces when it goes into the mixer and it subtracts from the frequency I'm interested in receiving, the output will always be 455 kilohertz. So that's what this little bit of symbolism is. You know, we have the sum of the frequency F1 and plus F2. So the frequency I'm listening to, or want to listen to, plus our local oscillator that's generated, the circuitry locally inside of the radio is generating frequency 2. So when we pass through mixer or heterodyning, we end up with a sum frequency F1 plus F2, but we're not just interested in that at all. So we discard that. We actually will filter that out. So when we add the two, you know, this is what we get, 28.200. I'm not interested in that frequency at all. What I'm interested in is I want to end up with 455 kilohertz. So frequency 1 minus frequency 2, if we were to subtract them, we will get 455 kilohertz. That's what we're interested in. That's what mixing or heterodyning is all about. So we say here, the difference frequency is what was used. The sum frequency is what we throw away, or we discard, or we filter out. And we put some numbers here to illustrate that. So if I'm trying to receive 14.250, so my antenna is bringing that in, I'm tuning a ham radio operator is on that frequency operating, I want to listen to him or her. That's where we tune our dial, right? We get 14.250. But the receiver IF frequency, we know it to be 455 kilohertz, very efficient at that frequency. So therefore, the local oscillator needs to be tuned in such a way that it produces output of the mixer 455. What is that frequency? Well, it's 13.795, because if we were to subtract 14.250, which is what I'm interested in, from the output that I'm interested to get to 455 kilohertz, we end up with 13.795. That's how we got that, right? So 14.250, subtract the final output, which is 455 kilohertz. We know that the oscillator needs to produce a signal at 13.795 so that we will get this as the output. And that's the match right here. And we just have another example here. What if we wanted to listen to 14.240, not 250 as the first example? You will just simply have to set the local oscillator to not 13.795, but to 13.785, because we have just dropped 10 kilohertz down. So therefore, the oscillator needs to adjust 10 kilohertz down to be able to receive the lower frequency, 14.240. So folks, hopefully this example has made it real in terms of the actual circuitry, and that we're not just theorizing in the sense of, okay, a conceptual view, but we're actually putting some numbers so you can see how the circuitry actually works to function, to bringing the signal into the radio, use a local oscillator to mix it or heterodyne, and we end up with a standard frequency for the intermediate frequency IF stage. So there's a problem when we use superhet or super heterodyne receivers and using the concept of heterodyning or mixing. And you probably sensed it already from what we discussed. You know, we actually get two outputs. One is not useful to us, or we are not interested in one. That's the problem right there, right? Because of that, we can also generate another signal, a ghost if you want to call it that, an image of the one that we're interested in. And that one that is generated actually happens to be twice the IF frequency away from the one that we're interested in, right? So that is actually an exam question. It'll ask you, you know, that interference signal that you get, you know, the unwanted frequency or that unwanted signal, how far away is that frequency from the wanted? And the answer is twice times the intermediate frequency away, right? So that's an exam question. It's actually the last bullet point. So you need to learn that for the exam. It's twice times the IF. But let's discuss this whole question or this problem of image response. What causes that image to be created in the first place? And it has to do with the fact that our mixer is actually, when it mixes the two frequencies, the way the mixer works is that it produces a summation of the two frequencies, and it also produces a difference of the two frequencies. but we are only really interested in the difference, right? So when we do that, we get two entirely different frequencies, right, that can produce the 455 as well. Because if you think about it, all we need is 455 output, but we have two frequencies, or there are two frequencies. I'm interested in listening to 14.255, for example. So if I were to mix that with 13.800 from our local oscillator, I will get 455 out. But if you were to check this frequency of 13.345, if I were to mix it with 13.8, I will also get the same 455. But I'm not interested in receiving this frequency, 13.345. I'm not interested in that at all. What I'm interested in is listening to the frequency 14.255. So if I'm listening to this frequency, my local oscillator, because I've tuned the dial to this frequency, produces the mixer frequency of 13.8, or the local oscillator frequency of 13.8, and the mixer is mixing it. It will also, if there's a signal that's present on another frequency, 13.345, it will take that signal and mix it also with the 13.8, and I will end up with 455 also. So that's the concept of image response. That frequency, that additional frequency, that the property is such that if it were to be mixed with my local oscillator frequency, will also produce 455 kilohertz. That is the problem right there. So what that also tells us is that the circuitry for a radio needs to be filtering. It needs to filter out this other frequency that I'm not really interested in receiving. Because if there's a signal, it could be some sort of noise, or it could actually be another legitimate frequency in use. My radio will produce two signals coming out of here. It will hear this frequency, but it'll also simultaneously listen to this one as well. And I do not want that. I'm not interested in this particular frequency to listen to. I'm only interested in listening to this one. But while I'm listening to this one, the local oscillator is generating this for the mixer. If this frequency that I'm not interested in is present also, it will mix, and I will get two signals coming out at the same frequency, which is not desirable at all. I'm only interested in listening to this one. So that is the problem of image response, because we might end up hearing two frequencies at the same time. The one we're interested in and the one that we are not interested in. So that behavior is called image response, and it's considered a type of interference because I'm not interested in receiving the other frequency. So we have to plan circuitry, we have to design circuitry to filter out this frequency from mixing inside of here, because if it only came in here, the mixer will dutifully do what it's supposed to do. It will mix this frequency, and then it will also mix this one, 14.255, and we end up with an IF of 455 kilohertz that combines. It will listen to these two frequencies, and we'll probably get some kind of interference or gibberish inside of there. All right. And as we mentioned before, an exam question is, well, at what frequency does that, or is the interference signal occurring at? And it is twice the IF frequency away from the desired signal, right? So that's an exam question. Right? We have a little diagram here to show, the local oscillator, the wanted frequency, and the unwanted. And we show here diagrammatically that the unwanted frequency is actually 2 times the IF frequency. Right? So hopefully this helps us to visualize that as well. So when you get the slides, look this over, meditate on it a little bit, and hopefully it will jump out at you and become a lot clearer. But these are the exam questions that you have here. Twice times the IF is where the interference frequency exists. All right, so another problem. So as hams, not only must we know what we are trying to achieve, we must also know about the things that are preventing us, or that will stand in our way or spoke in our wheel as we are trying to transmit or receive. So another phenomenon that exists that's problematic for us as hams is called intermodulation, sometimes just abbreviated as intermod. And what that is imagine that the mixer is what we call non-linear. Let's say it's not a very good mixer, right? Or it's not ideal. It has some properties where it's non-linear. When it combines the frequency we're interested in listening to with the local oscillator frequency, we may end up with some random frequencies on the output, and that could be quite a bit of a problem for us, right? So that issue with the non-linearity of the mixer, what it produces is considered or called intermodulation, right? So that's an exam question. So we also say that these frequencies are unwanted. The outputs, those unwanted frequencies, are also termed as spurious output or spurious signals. Right? So intermodulation, intermod, or spurious signals. Those are the terms that we will use to describe that unwanted, let's say, interference that is not desirable to have at all. So we need to be aware of it, and we need to do all that we can to prevent it. All right, so there's an exam question, the concept of odd order multiples of the original signal. So what do we mean by that? So we have a frequency that we are receiving our signal, or we could be generating a signal as well. And a multiple of that frequency is considered a harmonic of the original frequency. So you will have twice times the fundamental frequency, we'll have 3 times the fundamental frequency, and then you have other combinations of those, and those are considered harmonic. So you will hear second order harmonic, third order harmonic. So anytime you hear order, it just means multiply by whatever the number is. So if you have second order harmonic, you just take the frequency and multiply it by 2. If you hear third order harmonic, you multiply the frequency by 3. But there are some other combinations as well of the product of these frequencies that add to the intermodulation problem. And that's what this graphic is trying to illustrate in a way, right? So we need to be aware of intermodulation, and we also need to be aware that intermodulation can be caused at order frequencies of the original, right? Or what we call multiples of the fundamental frequencies, and we call that the order. So second harmonic or second order, third harmonic or third order. And there's an exam question that will come that we need to be aware of. So when we say odd order harmonic, it just simply means 3 is an odd number, 5 is an odd number. So the third harmonic is an odd order frequency or odd order multiple. The fifth harmonic is an odd order. So anytime you hear about odd order, you're talking about 3, 5, 7, and those sorts of numbers in terms of the multiples of the fundamental, or multiplying the original frequency by a number. So 3, you multiply by 3, so that's odd. You multiply by 5, that's odd, and so on. So they will ask you a question for an example of an odd order intermodulation product of 2 frequencies. So you have frequency 1 and frequency 2. So for the exam, it's the last bullet point here. The 2f1 minus f2 simply means you take frequency 1 multiplied by 2, and then you subtract frequency 2. So 2 multiplied by f1 minus f2. So please learn this. It's an exam question, and they will ask you, please give which is an example of an odd order intermodulation product of 2 frequencies, f1 and f2. The answer will be 2 times frequency 1 minus frequency 2. Right? So on your screen here, we have several examples of the intermodulation products of several frequencies, but the one that you need to learn is 2f1 minus f2. All right, so let's talk about multipliers as well, right? So of course, as amateur radio operators, we are using circuitry to listen to as well as transmit radio frequency. So sometimes we will generate, or we are able to generate a frequency inside of our radio, inside of our transceiver equipment. And then after we have generated that frequency, we need to multiply it so that we achieve another frequency. So that's quite often how circuitry works. So we want to get to 144 megahertz, somewhere in that vicinity as a frequency to transmit. But sometimes you do not generate that 144 megahertz frequency directly. You generate a lower frequency first, and then you use what is called a multiplier to multiply it so that you achieve the frequency that you intend to. So a good example is on the 2 meter band. And if we may recall from the technician class, the 2 meter band for amateur radio is between 144 and 148 megahertz. So that's the 2 meter VHF band. And we want to produce a signal at that frequency. But we may start in the circuitry, in the schematic, you may see a stage where a lower frequency is generated by the oscillator, right? Or the whatever circuitry is generating the frequency, a lower frequency. So it might actually start off by generating it somewhere in the 12 megahertz range inside of the radio. But you don't want a 12 megahertz frequency. What you want is 144. So some of you are probably already shaking your head and say, oh, okay, you want to get to 144 and you're starting off at 12. Well, just multiply it by 12 and you get 144 and you'll be quite correct. That's exactly how it works. The multiplier stage of the transceiver will do just that. It will generate at 12 megahertz, and then it goes into the multiplier stage of the radio frequency, the radio's circuitry, multiplied by 12, and you will end up with 144 megahertz. So this is what this diagram is trying to show you here. We start off by generating a 12 megahertz frequency inside of the radio. Then it goes to the multiplier stage circuitry inside of the radio, multiplies it 12 times, and then it outputs 144 megahertz, because 12 multiplied by 12 is 144. And then that now goes to probably an amplifier stage, and then it goes to the antenna itself, and you transmit that signal. So that's what this slide is all about. We're actually talking FF, frequency modulation. So you have an FM signal here. And we're also talking about the 2-meter band. So we start off with 12 megahertz, we multiply it by 12, and we end up with 144 megahertz, right? So essentially, when we use a multiplier, we are using a harmonic or multiple of the original frequency. Remember we said you have the first order harmonic, second order, third order, and so on. So anytime you multiply, you can consider us as also using a harmonic of the frequency to achieve or to attain the desired operating frequency. So we have it here mathematically shown. You start off with 12 megahertz, you use a multiplier of 12, and you end up with a signal of 144 megahertz, right? So that's how it works. So an exam question is the stage in a VHF FM transmitter, right? So you have different stages. You know, we have shown block diagrams of what a transceiver is, or a receiver or transmitter. So the stage where that frequency generates a harmonic or a multiple of a lower frequency to reach what you're trying to achieve. In other words, 144 in this case here is called the multiplier stage of the radio. So that's an exam question. You want to know what stage does the multiplication? It's the multiplier stage in your radio. All right, so let's just do a couple more slides before we take our break. So the concept of deviation and multiplier. So we just talked about if we're trying to generate a frequency of, let's say, 144 megahertz, we start off with a frequency of 12 megahertz and we use a multiplier to multiply it by 12. But the thing about it is that the multiplier stage in your radio does not only multiply the frequency of that signal, it also multiplies what we call the deviation, left and right of the center frequency. So if we are going to multiply right through, we also need to take that into account when we're generating the deviation at the lower frequency first. So when we generate that lower frequency, we also need to make sure that the deviation is also going to be multiplied, and therefore we do not over deviate at the first stage, because if we were to do that, by the time it goes into the multiplier stage, we would have over deviated. So what we essentially are talking about is taking into account the fact that the signal is going to end up in a multiplier. So it will multiply the frequency, yes, but it will also multiply the deviation. And because it's going to multiply the deviation, we do not want to over deviate. If you remember, we talked about over deviating. We might end up in exceeding the bandwidth. We might end up, if we're at the edge of a band, we might end up operating illegally because our signal is over deviated into lower than or higher than the band that we are licensed as amateur radio operators to use. So you do not want to over deviate your signal. So you're talking about FM signals here and you're over deviating and then you're operating illegally. We do not want to do that. So in designing our circuitry, or just for awareness as to how the frequency, the radio operates, we need to make sure that at the first stage, we calculate that, let's say we are using a 12 times multiplier stage, we need to make sure the deviation is 1/12 of what the intended output deviation will be. So we generate it first at the 12 megahertz frequency, for example. So by the time we multiply it by 12, we'll get the frequency of 144 megahertz, but the deviation will also be within whatever the specification of that signal is. So this essentially is telling us, this slide is telling us, take into account deviation when we are using multipliers. It's not only going to multiply the frequency, it will also multiply the deviation. And that's exactly what we have here as well. We are inputting a frequency, it's multiplying by 12, but it's also inputting a deviation for that frequency, and it's also multiplying by 12. Stands to reason? Okay. And here's an example calculation to hopefully make it real and bring it out. So, and actually, this is an exam question. So let's deal with it. So we are trying to apply this theory we have just learned in terms of calculating for the circuitry. We want to do, construct a circuit. So we have the various stages here in a block diagram. So you have the frequency multiplier, but we need to know a few things about it. And here's the exam question. What is the frequency deviation for a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation with a 146.520 megahertz FM foam transmitter? So that's a mouthful, but let's break it down. Let's dissect this question and see what they're asking us so that we could apply. It's actually a very simple question in the end, but they have put a lot of information here, and that's why understanding every single word and the context of each of these words are important. Let's deal and dissect first. They talk about a reactance modulator. So if we were to do this diagram here, and you see we did reactance modulator, we apply the audio signal, and then we have, you may remember when we talked about reactance modulator, we say we can use it to generate phase modulated signals, but you can of course also generate frequency modulated signals, right? So that's what they mean here by a reactance modulated oscillator, right? So they're giving us a lot of fancy terms, but we know, or we are aware from the last, oh, you're talking about generating an FM or PM signal, right? That's all this bit of that extra information is saying. It's FM, right? So we're generating an FM signal. But it's 12.210 megahertz, right? That's they want to know if we are starting off with this and then we're going and multiplying it to end up with a 146.520 megahertz FM phone transmitter. So again, let's dissect this. FM, frequency modulation, phone, that is voice. So that means we have audio input. So we want to end up with a 146.520 megahertz frequency, right? That's where we want to generate our transmit frequency on our radio. But the first stage is going to be 12.210 inside of the radio. But we also note here that this 146.520 megahertz frequency needs to be within 5 kilohertz deviation to be within the specification. So if we are going to generate first at 12.210, and we're going to end up with a frequency of 146.520 by the time we multiply it by some number, we also need to know that when we generate this frequency inside of the radio, to end up with a 5 kilohertz deviation after we multiply, we need to make sure that we divide this by some number so that when it's generated, it's not 5 kilohertz, it will be much less. But when it's multiplied by whatever the ratio is, we will end up with 5 kilohertz. So that is what this problem is asking us about here. What is the multiplier, right? We have to work that out. And then what frequency would we need to generate for the deviation so that when it goes through the multiplier, it ends up to 5 kilohertz. So the first thing that we need to work out is what is the multiplier? So we starting off with a frequency of 12.210, and we're ending up with a frequency of 146.520. So for us to know what the multiplier is, we simply divide this frequency by this one to get what the multiplier is. And that's exactly what we have here in the equation. 146.520 megahertz divided by 12.210 megahertz gives us 12. So you can check that for yourself, use the calculator, and you'll see that that 12 simply means that the multiplier stage, the frequency multiplier, is multiplying whatever it gets in by 12. But note, it's not only multiplying the frequency, it's going to multiply the deviation as well. So because we want to end up with a 5 kilohertz deviation, for us to figure out, working backwards, what should be input deviation, we need to divide this by the same 12, because when it comes in to the multiplier, it is going to multiply it by 12. 12, so we have to divide by 12 to know that the frequency that is initially generated, 12.210, what deviation needs to accompany this frequency. So we need to divide it by 12. So essentially we divide 5 kilohertz by 12. But 5 kilohertz is actually 5,000 hertz, right? So we're actually dividing 5,000 hertz by 12, and check it to yourself with the calculator. You will end up with 416.17 hertz. And that is actually an exam question, and this is the answer. So this is how you could either learn it or you could learn how to calculate it. And this is the calculation here. And these things here are just to give you a visual example of what we're trying to do. We are trying to end up with a frequency of 146.520 megahertz. We are starting off with a frequency of 12.210 megahertz, so we are multiplying by 12. But we also want to end up with a frequency deviation of 5 kilohertz. So what must the deviation input be, given that it's going to multiply it by 12? Well, we did this calculation, and we know it's 416.7 hertz that it comes in. It gets multiplied by 12, so we end up with 5,000 hertz or 5 kilohertz deviation. So hopefully this helps diagram what the question is and the solution. All right, so let's just do probably 2 more slides before we take our break. So bandwidth, you may recall when we talked about bandwidth, we equated that to cars, right? We say how many lanes do we occupy on the highway, right? So that is what bandwidth is about, right? And we showed that for different types of signals, it occupies a different amount of bandwidth, right? So CW Morse code, 150 hertz, single sideband, 3 kilohertz, AM, 6 kilohertz, and FM varies. It could be as much as 15 kilohertz and so on, right? And these are the number of lanes on the highway that your car, your vehicle is occupying, right? So more bandwidth, right? Bigger your vehicle. It doesn't speak to how many people inside a vehicle, but your vehicle is going to occupy several lanes on the highway, right? Starting from the smallest bandwidth to the larger bandwidth. So FM, of course, uses quite a bit of bandwidth, right? And we use FM on the VHF band and also the UHF band. And if you recall, in the technician class, we defined what VHF and UHF is, so you can refresh yourself. But we cannot use, or we do not use FM on HF because it requires too much bandwidth for the limited amount of bandwidth that we have in the spectrum on the HF frequencies. And remember, HF is between 3 and 30 megahertz. So again, this is important. So refresh yourselves as to what HF, VHF, and UHF is from the technician class material. And because that amount of bandwidth is necessary, we typically won't use FM on the HF part of the spectrum, but we will liberally use it on VHF and UHF. But we need to know how to calculate the bandwidth that is occupied by a particular signal. And this is our trusty bandwidth formula here. We will need to actually use it in a calculation. It's an exam question as well. So this cryptic looking formula is as follows. Bandwidth, right? So this is the equation, is equal to 2 multiplied by delta F, which is the deviation. So again, this concept of deviation is coming in, plus FM, and FM is the modulating frequency. So it's a fairly straightforward formula, but the representation of it might look a little bit cryptic. But when we do the example, you'll see how simple it actually is at the end, no matter how it looks kind of cryptic as a formula. So this is the equation for calculating bandwidth for an FM radio signal. Bandwidth is equal to 2 multiplied by the deviation plus the frequency. Right, so this is an exam question on your screen, and we have done the calculation here to see how we arrive at the answer. So again, in these exams, you can learn off the answer, but we try to go through the process of how do we get there. So you don't really have to learn the answer, learn the technique so that you could calculate it in the exam, right? With that, you have to actually remember a lot less, right? So once we understand the concept or the formula, then we can calculate just about anything. We don't have to remember the value based on what the question is, right? Okay. Question: what is the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulating frequency? So let's dissect this question. What are they asking us? They're asking us for the total bandwidth. So we know we need the bandwidth formula, but bandwidth for what type of signal, what mode? It's an FM phone transmission. So remember, FM frequency modulation, phone transmission in amateur radio. Anytime we hear phone, it's voice, right? So don't let all this extraneous information tie you up too much, right? It's an FM signal. We want to find out the bandwidth. But to use the bandwidth formula, we need some information. Have they given us that information? Yes, they have. So we write down the bandwidth formula. Bandwidth is equal to 2 multiplied by delta F plus FM. Did they give us delta F? Yes, they did. It's 5 kilohertz, right? That's the deviation. They give us the frequency or the modulating frequency. Yes, they did. 3 kilohertz. All of that is provided in the question. So we just need to plug it into our trusty bandwidth formula. Again, bandwidth is equal to 2 multiplied by the deviation plus the frequency. So we substitute the deviation delta F with the number 5 because the deviation is 5 and the frequency is 3. So they have given us here it is 3 kilohertz. So 2 multiplied by 5 plus 3, we get 16 kilohertz, which is the answer. So while it looks a little bit cryptic in terms of the formula, you realize the math isn't too bad. It's just simple addition and multiplication to get the answer. So you can go this over a couple times. I will encourage you to write down the question, write down the formula, and actually work it out on paper. And you'll see how it will grow upon you. All right. So folks, at this time, let's just take a quick 2-minute break. I said we will be going a little bit over because we're just trying to cover enough material here to make sufficient progress. So let's take a 2-minute break, take a stretch, get up. Let's have a bathroom break, maybe some water, refresh yourselves, and back in 2 minutes time. All right, so welcome back, everyone. All right, so hopefully this formula is straightforward enough. And right, so let's, this next slide is not really on your exam as such, but because we reference the mode called Pactor sometimes in between, we just have a slide up on a mode called Pactor 3, and it's a digital mode, right? So remember, anytime we use the term digital mode in amateur radio, we are saying that we are connecting a computer. So the computer does the talking as opposed to us using phone mode, which is our voice that we speak into a microphone, right? So this is just some extra information that you can have a look at on your own time. Right, so it's important for us to discuss the concept of duty cycle. What exactly is the duty cycle? So I like to think of the duty cycle when it comes to, well, okay, it's Christmas time, many of us might be making cake, and we may use a sort of a cake mixer or hand mixer to mix the cake, the ingredients, right? Now, sometimes we will have that cake mixer running for half an hour, 20 minutes, whatever time we need to mix the ingredients. And sometimes appliances have a duty cycle that if you were to read the instruction, they will tell you something like 5 minutes on, 10 minutes off. So what that means is that the duty cycle is not 100%. You have to use it for a little while, let it cool down and run again. So believe it or not, if you take the time, you'll be surprised. Look at hand mixers, blenders, any of those electrical type appliances. You may be very surprised that it's not intended to run 24/7, 100%. At least the domestic or the home version of those appliances. The commercial versions of the appliances may have, a bigger or larger duty cycle that you could run them for an hour at a time. Like microwave ovens, for instance. You could run those at home for a little period, but you may not be able to run it, for an hour. You might burn out the magneto, and it's really a commercial issue in the sense of building something that will last based on the usage, right? You can overuse, you can overdo. There's some things that if you use it continuously or constantly, it will not last, right? So it speaks to the quality of the item. It also speaks to the intended use of the item. So in amateur radio, we talk about duty cycle in the same way. So sometimes we have a transmitter, for instance. Maybe the output power of that transmitter is 100 watts. But it is not meant to transmit at that 100 watts for an hour continuously. You may be able to do 20 watts continuously for an hour, but you may not be able to do 100 watts continuously for 1 hour, even though the radio is capable of doing 100 watts. It's not 100 watts at 100% duty cycle. It may be 20 watts at 100% duty cycle, but 100 watts at maybe 10% duty cycle, right? So that concept of duty cycle is important because digital modes tend to require or have a higher duty cycle or transmit at a high power, sustained for a longer period than, let us say, phone modes when we are speaking. Speech, especially if we're using single sideband, is very bursty and so on. And the average power will not necessarily be the peak power. But on digital modes, whatever output power you say you set the radio at, it's going to be at that peak for the continuous time that the signal is transmitting. That's typical of digital modes. So that's why we need to know about it. So on the right hand side, we have a little diagram that visually shows what duty cycle might look like in a graphical standpoint. So 50% duty cycle. What is 50% duty cycle? Well, essentially it's running for half of the time. So maybe you have 1 minute on, 1 minute off, 1 minute on, 1 minute off. So that's like an example of a 50% duty cycle. It's running for half of the time, or it's running at peak for half of the time. A 10% duty cycle, well, it runs maybe for a minute and it rests for maybe 10 minutes, and runs for a minute and maybe rests for 10 minutes, or it runs for 10 seconds and rests for another. So you may have 30% duty cycle, 70% duty cycle, and as we go up, we are increasing the duty cycle. So let's say a car, for example, you may look at a car speedometer and see that it can do 220 kilometers per hour. But I don't think the car was designed for it to do 220 kilometers per hour for an hour continuously. I don't think so. You might be able to burst up to that if you need to overtake or you have some emergency or whatever. But I don't think the idea is that we max it out. And that's the concept of duty cycle. Maybe it will run at 80 kilometers per hour for an hour or two continuously. And maybe we could boost up to 120 kilometers or whatever have you, whatever is allowable in your jurisdiction. But the idea is it's not continuous. And these are the bullet points that we have here. The digital modes tend to have a higher duty cycle. And it could very easily exceed the transmitter's average power rating, right? Because of that continuous. And these are exam questions here. Right, so have a look at these bullet points, get familiar with the concept of duty cycle, because as a ham, you can essentially destroy your equipment if you were to run at a higher duty cycle than the equipment is designed for. All right, so let's talk a bit about symbol rate and bandwidth. So you may have heard about bits per second, baud rate, and symbol rate. Those are terms, especially if you're using any kind of data mode, a computer modem, or some sort of internet speed. You'll probably have heard some of those terms. But we need to be aware of the term symbol rate for amateur radio, because what we are transmitting are symbols. Whenever we send a digital mode signal, it's a symbol that we are typically transmitting. Now, a symbol can or may represent more than one bit, right? But the idea is that we are transmitting symbols. And for our purposes, we will say that a symbol or the symbol rate and baud rate and something called the modulation rate is the same, right? They're not exactly the same, so to speak. Persons with advanced knowledge will know they're not exactly the same, but for our purposes, we'll use them interchangeably. So symbol rate or baud rate, for our purposes, is the same, right? Which is this transition from one signal level to another. That is what we will define it to be, right? And what we need to know for the exam is that the higher the symbol rate that we use, the greater the amount of spectrum or bandwidth that is used for that signal. So anytime you see a mode or a signal that is using a higher symbol rate, you could automatically say, well, that means it's going to use more bandwidth. And that's an exam question. Higher the symbol rate, higher the bandwidth requirement. All right. So we now come to the concept of using filters in an amateur radio receiver context, and also to cater for noise that may be present. So sometimes you turn on your HF transceiver and you hear a lot of noise on the frequency, and you tuning the dial and you hear a lot of noise. Well, you can use filters. Sometimes they are hardware filters, and they're also digital signal processing type filters included in modern radios. And you may even see a symbol that looks like this on the radio, which are the filters, right? You can filter and focus in only on the signal that you want and use a narrow filter. So let's say this is noise on the frequency, but this is the frequency you are interested in listening to. You can use a narrow filter to filter out the noise. But if you use a wide filter, the wide filter will pick up the noise and you'll hear all sorts of interference while you're listening to this signal here. But if your radio is able to use that filter, you can remove the noise, because the noise is just a little adjacent to what you're listening to. But because your filter was too wide, you're picking up that noise. So that's why we say filters could be used to remove noise, right? So this is a visual example of visual representation. This is noise in this sort of this green here, and this is the signal we're interested in, and we use this filter so that everything outside to the left and to the right is rejected. If we use a wider filter like this one, notice that it incorporates some of this noise. So we use a narrower filter, notch it out, and just listen to only the signal we're interested in, and we reduce our noise. Right? Now in digital modes, when we're using voice modes or phone modes, our ears could be tuned to listening to the person speaking, and we could kind of try to ignore the noise. But in the case of digital modes are very sensitive, or can be sensitive to noise, depending, right? There are some digital modes that are better than others, but many digital modes, once there's noise, you tend to have what's called an error rate that can increase. And therefore, when that error rate is too high, you might get garbage or garbled text showing up on your screen. Remember, digital modes is using a computer to send and receive signals. So therefore, on your computer screen, you may be seeing all sorts of gibberish if the noise levels are too high. But you can use filters to try and correct that situation. All right, so one of the things for the exam that we need to know is that when we are using filters and we use it properly, and what we are trying to aim to do is to make the bandwidth of the mode, each mode will occupy or require a certain amount of bandwidth. When we match the mode's bandwidth to the receiver bandwidth, and they're matched one-to-one or as best as possible, that is the best case scenario, what we call the best signal to noise ratio that we can have, when we match the receiver's bandwidth to the bandwidth of the mode. So we use filters to do that matching quite often. And that's an exam question. We say when filters are used properly, the receiver bandwidth becomes matched to the bandwidth of the mode being used, and it results in the best signal to noise ratio. Exam question. All right, so again, let's remind ourselves what a digital mode is, right? So we have a computer, we may have some sort of interface, and we connect it to a radio, and our radio is connected to our antenna. So this is what we mean by a digital mode. We use a computer to do the talking, right? So one of the digital modes is PSK31, and you may remember from last session that we said PSK is phase shift keying. So we need to know that PSK is one of the digital modes that we will encounter in amateur radio. It just happens to use a symbol rate of 31 baud or 31 symbol. And it is called PSK 31 because of that 31 baud specification. Now that's fairly slow as a mode, but it can communicate. All right, so the other thing that we need to know for the exam about the mode called PSK 31, right? Phase shift keying 31, right? It uses 31 baud. That's the symbol rate. Is the fact that PSK 31 uses varicode, right? And what is that? What exactly is varicode? It is using a symbol or a character to represent many values, right? So for example, notice on the right hand side here is an example of varicode. If I use the letter E in this case here, it means 1 1. If I use the uppercase E, it means 1 1 1 0 1 1 1, right? If we use the letter O, lowercase o, it's 1 1 1. If we use the letter T, it's or lowercase t, it's 1 0 1. So this is what we mean by varicode. We are using a symbol to represent multiple values, right? What it allows us to do is that we can send several things by sending one symbol. So imagine you send the letter E and you're actually sending 1 1, right? So that's a very efficient way of sending or utilizing your signaling by using varicode. So let's read the last bullet point because it's an exam question. Varicode is designed in such a way that more frequently used characters, there are some letters in the alphabet that are more frequently used in sentences or in amateur radio communication. It uses fewer bits and it also will use less time. Whereas the ones that are less frequently used will be things like uppercase characters, and they will use more bits and take longer to transmit, right? So this is what varicode is. All right, so let's talk a bit about RTTY or RTTY. It stands for radio teletype. RTTY is another digital mode, as we are seeing on your screen here. It says another digital mode is RTTY, RTTY, radio teletype. And again, it's a digital mode, so that means that you have a computer that is interfaced to your radio. For the exam, we need to know that RTTY uses what is called the Baudet code. Now, some people pronounce it differently, so it's really pronounced Baudet, but some people say Bordeaux or Bordeaux, you know, but it's really Baudet. Baudet code, and Baudet code uses 5 bits per character. So for every character that you send, remember we were showing varicode before, where you use a different number of symbols to represent a particular letter, for instance, right? So this is varicode here. If you want to send an E, this is what you have to send, 1 1. And notice for the more regular characters, they're shorter, right? So that is intentional, right? Notice the less used characters, they tend to use much longer characters to represent, right? So if you want to send an M, you have to send all of this 1 0 1 1 1 0 1 1. If you want to send a lowercase m, it's just 1 1 1 0 1. And because the length is different, that's why they also call it varicode, right? It's variable in terms of the code. You can think of it that way. But with respect to RTTY, it uses 5 bits per character. So no matter what the character is, it uses 5 bits. And we need to know that there's also a start bit and a stop bit. And those are actually exam questions that you will encounter. The other exam question in relation to RTTY or RTTY is that RTTY uses FSK. I remember from our last session what we said FSK was. It means frequency shift keying, FSK. And that FSK is used to send the two signal levels, which is the ones and the zeros, also known as marks and spaces, right? So RTTY uses FSK. And by the way, we have been included, probably if kind of, in the interest of time, we're kind of phasing over it, but this here, and we'll come to the concept of a waterfall display in a little bit. This is what it actually looks like on the waterfall display, these various signals. So this is a RTTY signal. Previously here, we had a PSK31 signal, and we'll show you what like an FT8 signal looks like. So these are the waterfall displays. It's kind of zoomed in. So sometimes when you look on your computer or even your radio that has an LCD display, you can actually see the signal itself, the digital mode signal looking like this, right? So this one is RTTY, and you can see here, right, you will be able to listen to it, but you will also have a visual representation, or what we call a waterfall display version of the signal itself. You're not only listening, your computer is not only decoding it, but you can see it visually. That's additional information for you. All right, let's see if we could barrel through these couple of slides. Right, so another digital mode called WSPR, sometimes people pronounce it as whisper, right? So what is WSPR, right? It stands for Weak Signal Propagation Reporter, WSPR. And it is actually used to check your propagation. And what do we mean by that? How is our signal able to get to another part of the world, for example? Is it through an efficient path via the ionosphere, maybe a particular frequency, date and time, and the sunspot cycle between Trinidad and Tobago and, let's say, North America? The signal is very good. We have good propagation, as we'll call it. Propagation is nice. WSPR is a mode where you have beacons or stations that are transmitting and others that are receiving, and they will report on those reception on a website. You can look, for example, on this website on your screen, where you will see all of the beacons and the stations that have listened or received the beacons, and this will give you a good proxy for how propagation is going. So you can conclude from this location, you might be able to communicate with all of these locations because it is receiving the beacons and vice versa. So that is one way we can interpret the map for the WHISPER site. It's wsprnet.org, and you can see a visual representation of propagation. So that is one use of WHISPER or WSPR. It shows you real time the potential for your radio signal to be received, or for you to receive a radio signal from different parts of the globe based on the conditions or propagation that is possible. So these transmitters are relatively low power transmitters, and they broadcast, literally, they transmit, and when they're received, they're displayed on the map for you to go and see what propagation conditions are like. All right, so just some additional information about what WHISPER is. It contains a transmitting signal of the station that is broadcasting or transmitting, and as well as what is called grid locator. So each location on the earth has a combination of letters and numbers, and they call that a grid locator. And of course, the signal level or the signal strength will also be known by the receiver, and it is displayed in dBm, which is decibel in reference to milliwatt. Okay, so the other point to note about WHISPER is that it can really detect low signals, or signals where it's within the noise floor and they have poor signal to noise ratios, all the way down to minus 28 dB. So there's just extra information for you to let you know that this mode is very efficient. It works really well. Another website that you can use is PSK Reporter. You can Google it. A pretty nice site that you can see amateur radio operators communication real time, and that is a good proxy for propagation, or how possible it is for signals to go from one location to the other based on the time of day, the sunspot cycle, and general conditions that apply to radio communication, especially HF radio communication. All right, so sticking with the whole concept of digital mode communication, the other mode that we talked about that we use in amateur radio, it's a very popular mode. It's called FT8, Foxtrot Tango 8. And on the right-hand side here, it's what the FT8 signal looks like. Right. So this is what may appear on the waterfall display of your computer or your radio. But FT8 is also a weak signal propagation mode, or what is, it's not a low powered mode necessarily. You can run pretty much you can run high power. And in amateur radio, we say use no more power than is necessary to receive and transmit your signal. But it is really good in low signal conditions, or where your signal is very much into the noise floor. So it's optimized for that weak signal propagation. Right, so it's very popular right now. Many amateur radio operators are using this mode. As you become licensed, this may be a mode that you would want to get involved in. And on the right hand side here is what this software looks like, or one of the programs that's used, WSJTX software. This is the interface, or the GUI, graphical user interface, where you see the signals from the various stations that are communicating, and this is what you will actually use to initiate the communication. Remember, in digital mode, you're using a computer with software to control the radio. So this is the interface, and you will click OK, transmit. You will see the signals that's coming in, and you may choose who you would like to communicate with, and so on. All right, so a couple of exam questions. FT8, it's a digital mode. Digital mode meaning it uses a computer, and it's capable of low signal to noise operation. So the last bullet point is important because it's also an exam question. So we need to learn this off. An FT8 signal report of +3, what does it mean? It means that the signal to noise ratio is equivalent to +3 dB for a 2.5 kilohertz bandwidth. So you need to learn this for the exam. What does a +3 signal report on FT8 means? When somebody say +3, it means that your signal to noise ratio is equal to +3 dB, as in decibel, right? For what? A 2.5 kilohertz bandwidth, right? So this is an exam question in relation to FT8. Right, so you could read this first bullet point on your own time as to what FT8 is. We already discussed previous class what is FT8. So we now come to the concept of a frame in digital mode, such as packet radio. Right. So when we are communicating digital modes, we are essentially sending ones and zeros. But those ones and zeros are organized in a particular way called a frame. And part of the frame, a couple of the bits is called the header. So we need to know what the header is for the exam. So we don't need to learn all of this, but we're just showing here that a particular communication, when a digital mode is used, you have a frame, and you'll have different parts of that frame. And this frame contains all of the ones and zeros that are sent over the air. The computer generates the ones and zeros, sends it as a signal to the radio, and the radio transmits them. But there's a sequence. So it will send some bits, and then some more bits, send some more bits, and so on. But there are sections within the list of bits that have names, and we need to be familiar with a part of this frame called the header. And specifically, we need to know that the header, which is part of this overall frame or packet, is used. What is the header used for? It is used to handle the packet and to route the packet. That's all you really need to learn for the exam, the purpose of the header. But we have given you that bit of extra information so you can see what a frame actually looks like, right? This packet here contains various components. The payload is actually the content. You have what you call the checksum, and then you have some flags and stop bits and stop bits and that sort of thing. But inside of here, very early on, part of this frame is called the header, and it contains ones and zeros that allows or tells the endpoint how to handle this particular frame and how to send it, where to send it to, or to route it. This is the exam question. Header is used to handle and route the packet. All right, so we did say we're going a little bit over time, folks. So let's press on. So digital modes. So we have a couple of other modes, like Pactor and Winmore. So as an amateur radio operator, you may encounter those modes, right? So we need to know a bit about these digital modes. So Pactor is one that we use in amateur radio. Again, it's connecting a computer to the radio, just like all of the digital modes tend to be. Sometimes you have radios where the computer is built in. So you have an LCD display, and you say, well, wait, I'm not seeing that amateur radio operator. He's not using a radio at all to do RT. Well, the computer is in the radio. That's that convergence that exists. Or you can have a standalone connected computer with the signal lines for computer control as well as audio back and forth. So one of the modes is called Pactor. And there is a sequence when we are communicating, and there is a feature called a NAC response. When you get a NAC response, or NAC actually stands for negative acknowledgement, it means that you are requesting that packet or the data to be retransmitted. So that will be an exam question. What does NAC means? It's saying, please retransmit or resend that bit of information, because maybe the computer didn't get it or it was corrupted, and it sends a NAC sequence, negative acknowledgement. Please resend the transmission. We also need to know what happens when there's excessive transmissions that are occurring. So there's a time limit to things. A transmission is sent, a transmission is resent, it's resent again. And if you have too many of those transmissions, or what we call excessive transmissions, there will be a failure in the communication, in that the communication will be dropped. So that's another exam question. They'll ask you what happens when there are excessive transmission. You end up with a dropped connection. Right. So another exam question related to these digital modes is the whole concept of ARQ, or what is called automatic repeat requests. So sometimes when you are communicating using a digital mode, you have the two ends, you have the transmitter and the receiver. The two amateur radio operators are communicating via whatever the mode is. And there's an error that is encountered in that communication between the two computers or the two stations. That mode may allow for an ARQ request. What that is, it will say, you know what, I have not gotten that transmission clearly. Please resend that particular piece. That is considered part of error handling. So that ARQ means automatic repeat request. And what that does is request a retransmission of the frame that was dropped or was not received or was corrupted during transmission. So another exam question, what is ARQ? It means automatic repeat request, and it means that you are requesting the packet to be retransmitted. Right, so another term that we need to use in respect of digital modes, right? So these digital modes can be quite intelligent, right? The software will issue instructions via the radio frequency to do certain things. But one of the very powerful capabilities in using digital modes, built in some of them, is the ability to correct errors. Yes, you can detect errors and you can even correct them. Now, sometimes you have to include extra information in the packets to allow for error correction, but it can be done. And there's one called FEC or FEC. And for the exam, you need to learn or know that FEC means forward error correction. What is that really? Well, you include enough information inside of there that will allow the error to be detected and also corrected, right? So how it does it, it includes additional information, or what we call redundant data, that is transmitted along with the main information. So in case parts of it, let's say, gets garbled, it can use that redundant data to recreate the original sending source data. And that is called error correction. So that's not retransmitting per se. It's already included, you didn't drop all of the data. You have enough that you could recreate or correct the data. So that is called error correction. And the one that we are talking about here for the exam is called FEC, forward error correction. All right, so just a couple more slides, folks. We're almost through. So we did say that to use digital modes, we need to have software that's running on our computer to be able to send those signals. Even though we're not speaking into the radio, but we want to communicate, we either type or we click on buttons and the computer will do the talking. It will send the signal via the audio lines to the radio, and the radio will dutifully transmit those signals, digital mode signals. So software, for example, will be things like FLDG, which is very popular for PSK31, and for FT8, very popular mode, WSGTX. So we have a screenshot coming up shortly to show you what WSGTX looks like. And also we did say that we needed to discuss the concept of a waterfall, and we have been showing on your screen what the various digital mode signals will look like on screen, and that screen is called the waterfall, right? You'll see the digital mode represented by color bars and nice graphics, and each mode will look a bit different from each other, and that screen that is used to see a visual representation of that audio signal or that RF radio frequency signal is called the waterfall, right? So we'll come a bit to what the waterfall display actually looks like, but for now it displays the signal strength of the particular transmission. It will show you the frequency, and you get that on the horizontal scale, and it will tell you the time on the vertical scale. So as every second goes by, you'll see the waterfall scrolling usually downwards. So that's why we say on the vertical scale will be time. That will become a little clearer when we show the actual screenshot, right? Which is our next slide. One of the things that you can easily see, remember we talked about the concept of overmodulating. If your signal is overmodulated, you're cresting, you're clipping, you're clamping, on the waterfall, you'll be able to see that visually, because on either side of the signal, you have nice, strong vertical lines, right? So let's take a look, right? On your screen here, that's an example of the vertical lines. You see them here? That means you're overmodulating. There you go. That's what an overmodulated signal looks like, with the two vertical lines here. But we need to know, we need to be aware of what the waterfall is and what it looks like. So this is WSGTX software. So we're doing FT8 mode. But this section of your screen here, you notice all of these here, these are actually signals. So on the horizontal axis is the frequency, and the vertical axis is time. So this waterfall actually scrolls downward this way. It's scrolling down as time passes. So that's why we say the vertical axis is time. The horizontal axis is frequency. So this is one signal here. This is another signal. This is another signal, right? So you notice each signal has a bandwidth, right? So look at how many signals in a relatively short bandwidth, right? Many signals. And the stronger the signal is, you notice that it tends to go more yellow and red, right? And the signal that is weaker, it tends to be less yellow and more into the blue and greens. So this visual representation is called the waterfall, and it will show us the signal strength. So the more prominent it is, the stronger the signal is. The less prominent it is, so notice this signal here, right here, for example. This is a weaker signal because it is not as prominent as this signal. This is a stronger signal. So this is the waterfall, and we're seeing many signals. All of these are individual signals. This is a signal, this is a signal, and a signal occupies a finite amount of bandwidth. Right, so this is the bandwidth here for the signal. This is the bandwidth for the signal. Look at the signal here. This is the bandwidth for it. There's a signal here, but it's very weak. There's a signal here, but it's very weak, right? Look at another signal here that's pretty weak. Stronger signals here, right? So this waterfall is what you can have, or you can see it sometimes on some radios that have liquid crystal display screens. You can see the waterfall. And on a computer, you can see a much larger representation graphically of that waterfall. And you can see where signals exist, where transmissions are occurring. And you can also select to say, here, what I want to transmit in this part of the band, because there's a signal here and that's where I choose. Or maybe this part of the band is clear. So I want to put my signal on transmit here, which appears to be clear, right? It's not necessarily clear, but it's appearing that way. So this is the waterfall display that we keep talking about. And we talk about the digital mode, and we look at our radio for the waterfall, or we look at our software for the waterfall. This is what it means. Waterfall, because it, yes, in a way, it looks like a waterfall. This is scrolling downwards continuously as the signal is received. So we had shown this slide at a previous session, but this is just another one showing the WSGTX software. And this is the PSK Reporter website that shows propagation real time, or signals that are occurring between amateur radio operators real time. All right, so just before we go into the question pool, this is a bit of an announcement. We haven't yet come to this section in the course, but there are 2 questions in the question pools that have been withdrawn. So we will keep this slide running for the next couple of sessions, but I just thought it would be useful to announce to the participants that we have these 2 questions, questions G1C08 and G1C10, that have been withdrawn from the question pool. In the No Nonsense Guide, it's on pages 135 and 136. But we did show how to read the question pool. So you're looking for G1C08 and G1C10. Those are no longer going to be part of the question pool, and they're no longer going to be exam questions. So just bear that in mind. We will not be going through those questions in the course. But just to let you know, the reason why they were withdrawn is because those are related to what we call symbol rates, maximum symbol rates permitted on amateur radio. And the US recently passed legislation to remove those restrictions. So that's why these are no longer valid questions in the question pool. So let's go quickly to our question pool review. Right, so today we would have covered pages 46 to 53 in the No Nonsense General Class License Study Guide. All right, so this is our question pool review. Let's see if we can speed through this, right? We covered all of this theory. What is another term for the mixing of 2 RF signals? And we said mixing is heterodyning. Okay, what is the combination of a mixer's local oscillator and the RF input frequencies that's found in the output? Well, that combination is you get both the sum of the 2 frequencies as well as the difference. Next question in question pool, which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? Let's dissect this. What are they asking us? They're asking, in a mixer, you have the input frequency from the antenna, and we also have a local oscillator frequency. We mix both of them to get the IF1 frequency output, no matter what the input signal is. So that frequency that is varied using our tuning dial is called a local oscillator. What is the term for interference from a signal at twice the IF frequency from the desired signal? So we did say that this is where that was important. We said we need to know that twice the IF frequency, the interference that is caused by that frequency, that is 2 times the IF frequency away, is called image response. What process combines 2 signals in a non-linear circuit? So that's the keyword here, non-linear circuit, to produce unwanted spurious outputs. We did say if the mixer is operating in a non-linear way, that interference is called intermod or intermodulation. Which intermodulation products are closest to the original signal frequencies? So we did say it was odd order, right? So odd order is the answer to this question. Right? Remember what odd is? 3, 5, and so on. Okay, which of the following is an odd order intermodulation product for all frequencies F1 and F2? All right, so we did say we needed to learn this. So you have 2 frequencies, and they're asking for an odd order intermod. It's 2F1 minus F2. That's the correct answer. What is the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? So if you have a lower frequency signal and you're trying to get a much higher frequency signal, let's say HF you're generating, and you want to get a VHF, you multiply that signal. So therefore the stage in that transmitter is called the multiplier stage. What is the frequency deviation of a 12.210 megahertz reactance modulated oscillator in a 5 kilohertz deviation 146.52 megahertz FM phone transmitter? We did dissect this question and we did it as a worked example, so we didn't spend much time on the question pool review on it. We showed the calculation and the correct answer was 416.7 hertz. So please review that slide or the recording if you need a further to go back over how we got to this answer from this question. All right. Bandwidth related question. What is the total bandwidth of an FM phone transmission having 5 kilohertz deviation and 3 kilohertz modulating frequency? Well, we simply have to use the bandwidth formula. When we plug that in, we get the answer of 16 kilohertz. Next question in the question pool. Why is it important to know the duty cycle of the mode you are using when transmitting? So we did say duty cycle is important to know, especially for digital modes, because some modes have high duty cycles that could exceed the transmitter's average power rating. In other words, you want to know, you don't want to mash up your equipment. Next question in the question pool. What is the relationship between transmitted symbol rate and bandwidth? So we said that the higher the symbol rate, the more or the wider the bandwidth required. Right. Okay. Why is it good to match receiver bandwidth to the bandwidth of the operating mode? So this has to do with noise and so on. So it's because we want to get the best signal to noise ratio. All right, let's continue. What type of code is used for sending characters in a PSK31 signal? So you said varicode is what is used. Yeah, look at the distractors. All right, next one. Which of the following statements is true about PSK31? So we said that the uppercase uses longer varicode bit sequences and thus slow down transmission. So lowercase characters use less number of bits. The uppercase or capital letters will use a longer number or more number of bits. And because it's more bits for those, it will take longer to do, and therefore the transmission is slower. That's all this is saying. All right, which of the following requires baudit code, right? Well, we did say it's, let's restate the question. Which of the following describes baudit code? It's a 5-bit code, and it also has an additional start bit and a stop bit, right? How are the two separate frequencies of an FSK or frequency shift keyed signal identified? So remember those ones and zeros, it's a mark and a space. Right. Which digital mode is used as a low power beacon for assessing HF propagation? So we said that is whisper or WSPR, weak signal propagation. Right. Which of the following narrowband digital modes can receive signals with very low signal to noise ratio? Right, so sometimes signal to noise ratio is abbreviated SNR. Right, so we did say that that mode is FT8. Actually, that's the hallmark of that mode. Very low signal to noise ratios. Ratio signals can be heard and interpreted. All right, sometimes you're listening to the FT8 frequency and the signal and you're not hearing anything, but your radio is picking up the signal and your computer is decoding the signal and you're seeing all of the text on the screen. You wonder like, wow, I'm not hearing anything, but the radio is picking it up and the software is decoding it. Next question, what does an FT8 signal report of +3 means? So we did say the +3 means +3 dB, right? So the signal to noise ratio is equivalent to +3 dB in a 2.5 kilohertz bandwidth, right? What part of a packet radio frame contains routing and handling information? So we did show visually what the frame looks like, but we were interested mainly for this level and the course, the header is what will contain routing and handling. In an ARQ mode, what is meant by a NAC response to a transmitted packet? So we said that that NAC is saying to us, please resend the packet. So it is requesting a retransmission of the packet. That's what NAC means. What action results from a failure to exchange information due to excessive transmission attempts when an ARQ mode is used? All right. So we say if that occurs, the connection is dropped. All right. Couple more questions, folks. How does forward error correction, or FEC, allow the receiver to correct data errors? Well, how it does it is because it transmits redundant information along with the data. So that is what allows forward error correction to work, to correct data. All right, so you don't get something for nothing, right, folks? All right, which of the following describes a waterfall display? So we did visually represent it, and we also gave some textual definition of it. So it's the frequency is horizontal, and the signal strength is the intensity, and the time is the vertical scale. So that is what a waterfall display is. Frequency in the horizontal scale, signal strength is how bright or how intense it is, and the time is in the waterfall scrolling itself, which is vertical. Last question, which is indicated on a waterfall display by one or more vertical lines on either side of a data mode or RTTY signal? So we said when you see those strong vertical lines, it means that you are over-modulated or over-modulating. All right, let's quickly switch back to our slide deck. And so folks, I really do appreciate the extra time. We've gone about half an hour over. We know it's weekend, so we do appreciate that time. We're just trying to cover all of the material, right? So pages 46 to 53, what we covered today. Again, for those who want to know how to interpret the question pool numbers, this is a little chart to tell you what each of the things that look cryptic on the question pool means, so you can review this. We did say there are 2 question pool questions that have been withdrawn. All right, so we'll continue to mention that because those are no longer valid for the exams. So folks, you can send your questions to this email address or via WhatsApp to this phone number. We do have a WhatsApp channel. We have had it for a little while now. We've seen many of the students have joined the channel. If you have not yet, please consider joining it. It's an additional channel to get information about the course as well as other content that hopefully you will find interesting. So that's the link. You'll get it in the slide deck, or you can take a quick snap of it, or you can write it down very quickly. We'll leave it up for a couple of seconds again, but feel free. You're welcome to join that WhatsApp channel. So folks, our next session will be next week, Friday, which is the 29th of December at 8:30 p.m., right? So we're not really taking any breaks, folks. We'll try just to barrel through because we want to get to the point where we've completed all of the information necessary for you to take the exams in the shortest possible time. So we're just barreling through. We know it's holiday season, but we'll continue, and hopefully all of the recordings sticks so that if you happen to miss it, you won't really miss out because you will be able to play back the recording. All right, so that's the slide with the session next date. So folks, thank you very much for your time, especially for the overtime this evening. And given, I mean, it's Christmas time, I want to wish everyone season's greetings. Merry Christmas, everyone. Continue to be safe, do enjoy, and take good care of yourselves. And hopefully we'll see you back next week. Have a good night, all. Take good care.